Good morning, everyone. I hope that you guys are having a great start to your week. I hope that you enjoyed your weekend. I hope that you got a good week planned ahead of you. What we're going to do today is we're going to talk a little bit more about some hemoglobin. What we're going to get into with respect to hemoglobin is some more of the nuances of how hemoglobin behaves differently from myoglobin and those oxygen binding curves for hemoglobin, how they vary a little bit from the oxygen binding curves of no, the learning objectives are not still in progress. They are on your Canvas page, but I have not linked them. I'm not going to take a minute to do that right now, but they're up. If you go to the pages, I think you can see all the pages that, but again, I have a different access to the Canvas site from yours. I believe that you have pages access, and it is published, but they are up. There's about 30 of them. I tried to make it a little bit more concise so you had, here's what I can jump off from. If I was going to make 30 questions of this material, here's where I would make my 30 questions. So, at any rate, we're going to be talking about hemoglobin and myoglobin, what makes them a little bit different. And with all that said, let's just cut to the chase and let's get going. So, more allosteric effects. That's what we're going through. So, oxygen concentration and P50. If you remember P50, that was the concentration or the partial pressure of O2 that gets your hemoglobin to about 50% saturated. And whenever I say about, I mean exactly 50% saturated. One thing that is kind of tricky to think about with respect to this is that we're talking about not just one hemoglobin protein, but lots of them. So, so we're talking about a large population of those proteins. So it's not just a singular protein. Now, PO2, the partial pressure of O2 is basically the concentration of that oxygen in a particular environment. So in the veins, the partial pressure of O2 is approximately 30 torr, whereas in the arterial blood, it's about 100 torr. Now, myoglobin shows absolutely no cooperativity. If you remember at the end of our last class period, we were talking about positive cooperativity. That was where one subunit of hemoglobin will bind O2, and then all of a sudden the second and third and fourth become more inclined and interested in binding O2. Myoglobin as a singular protein, as a monomer, exhibits no cooperativity, whether that's positive or negative, because that singular myoglobin protein binds O2, done. Myoglobin typically has a P50 of approximately 2.8 torr. Hemoglobin shows cooperativity. Specifically, it shows positive cooperativity. And the overall P50 for hemoglobin is approximately 26 torr. Now, hemoglobin has only two quaternary forms, the T state and your R state. Our T state being our deoxygenated and our R state being our oxygenated. And our T state is our deoxygenated and inactive form, whereas our R state is our oxygenated and active form. Now, that T to R transition must occur simultaneously at the interface of the two alpha beta dimers, so the dimer of the dimers. Now, that first O2, this is the subunit that has basically the lowest affinity for binding O2. This has or that first subunit has a P50 of approximately 30 torr. The second O2, whenever that binds, that really initiates your T to R transition. The interface is destabilized enough for the T to R transition to actually kind of motivate and take place. The third O2, that binds a little bit easier. So it's that third subunit that binds O2 where we really see that big transition, and that has a P50 of approximately 12 torr. So our P50s for each of our subunits, those are going down. So you can kind of think about that as the demands, the requirement in order for this to be at 50% saturated. So there's a higher standard, and I'll use standard. There's a higher concentration requirement for the first subunit to bind O2, then for the third and the fourth, or for the second, third, and fourth. Finally, whenever we get to our fourth O2 binding, we're going to see a P50 of approximately zero point 0.3 torr. So one of the things that I want you to take away from this, and I'm going to write this on the slide, is that our P50 trends downward as more subunits bind O2. So that's one of the things that I want you to take away from this. And that's really illustrating um, the positive cooperativity. The third, fourth, those subunits are much more apt and able to bind O2 than the first and second. Um, in or as a result of the protein undergoing conformational change. Now, clear all that. How does this positive cooperativity binding take place? So when we think about oxygen transport, our oxygen concentration is going to be the highest, or our partial pressure of O2 is going to be the highest in the air that we inspire. So if we have a PO2, or the partial pressure of oxygen in the air that we intake, it's got a concentration, or a PO2, of approximately 158 torr. Now, one thing that I always want to stress to everyone is that keep in mind that a P50 is something intrinsic to that oxygen binding protein. It's a property that that oxygen binding protein has. So it's basically saying, in order for me to be 50% saturated, I need an O2 concentration of blah. Now, what we're looking at right here with this table, or with this, yeah, this table, is this is telling us what is the O2 concentration in these circumstances, in these environments. So inspired air has a partial pressure O2 of approximately 158 torr. Once it gets into the alveoli, so in our lungs, in the alveoli, the O2 concentration is about 100 torr. So the oxygen concentration has gone down a little bit. Now, keep in mind, we have not yet mentioned any hemoglobin binding this or anything like this because we're not really concerned with a P50 right here. Arterial blood has a PO2 of approximately 90 torr. So this is where all of our binding is going to take place. We need to give our proteins a very high concentration of O2 so that those hemoglobin proteins will bind O2. So basically, we're just trying to saturate hemoglobin as much as we possibly can by giving it tons and tons of O2. Now, if you think about, and we go back to the previous slide, what we were looking at was, I'm going to draw your attention to this right here. Our overall P50 for hemoglobin is about 26 torr. Okay. So what that means is, and just as a little bit of a refresher, what that means is that when the oxygen concentration is 26 torr, 50% of hemoglobin is saturated, or is, sorry, hemoglobin is 50% saturated. Now, let's clear all that. We go back, all of these are above that. So if we're talking about a hemoglobin population, say 1,000 proteins, 1,000 hemoglobin proteins, if you give them that concentration of O2, well, more than 50% of them are going to be saturated, or sorry, more than them are going to be 50% saturated. A very high percentage of them are going to be saturated or very close to saturated because that's where our binding is going to take place. We want to give hemoglobin proteins as much oxygen as possible so they can take it from our alveoli in our lungs and perfuse it throughout the rest of our body. Whenever it gets to other parts of our body, we want to, and we're interested in what is the capillary, interstitial, and cytosolic O2 concentration. Well, those O2 concentrations are considerably lower, 40, 30, and 10. Now, our hemoglobin protein that has an overall P50 of 26, whenever it gets to the capillaries, okay, well, its P50 is still lower than the O2 concentration in the capillaries. So chances are it's going to be at least 50% saturated. When it gets to the interstitial tissue, okay, the O2 concentration is still a little bit higher, so it's still at least 50%. But then once it gets into the cytosol in a cell, our O2 concentration is lower than that. So chances are that hemoglobin is much more readily able to deposit that and release that. It's in the capillaries, the interstitial tissue, and in the cytosol. And these are all kind of like the capillaries. We're getting to a smaller and smaller vantage point in view there, where then hemoglobin says, okay, the O2 concentration, I'm looking around and I can see that the O2 concentration is super low. So I can't hold on to all of my O2 anymore. So I'm going to deposit some and I'm going to release this. And as soon as I release it, then I'm kind of like, ooh, this isn't really a safe place for me. So I got to get out of here because I prefer to have all four O2s bound. So this positive cooperativity and this cooperativity in general is designed to release O2 at low partial pressures of oxygen. Now, so basically it's dumping a little in capillaries and yeah, that's a great way of looking at it. So think about it almost, I love that you phrased it almost like a progression. So as soon as it arrives in the capillaries, then it's like, okay, I can release some. And then in the interstitial tissue, it can release a little bit more. And then when it gets to the cytosol, then it's like, gone, get out of here. So great phrasing there, Andrew. I really like that. Now, allostery. Keep in mind, allostery and allosteric. There are lots of different proteins that are allosteric proteins. And what that means is that they basically have two different shapes. Allosteric meaning other shape. And I think that I'd be wrong if I believe that it's Greek. It might be because whenever I think allos, A-L-L-O-S, I think but that might be allo space steri. So at any rate, this means other shapes. So one of the things that we have to keep in mind is with respect to allosteric proteins, they are very tightly regulated. And one of the ways in which they're regulated is with what are known as allosteric effectors. I want you to really take this phrase and think about this one. An allosteric effector. Okay, so an allosteric effector is going to bind to an allosteric protein. Okay, not too much of a stretch there, but binding of an allosteric protein effector at one site affects the binding properties at another site. Okay, so let's think about this. Hemoglobin is a protein that, let's imagine that we have that T state of hemoglobin. The T state of hemoglobin, I'm going to go ahead and label this as HB sub T. Thank you, Andrew. Great, great. So the T state of hemoglobin binds to O2. And let's imagine that we're talking about one of our four subunits of O2. So our T state of hemoglobin binds O2. The first subunit binds that O2. What happens to the other subunits? And their kind of, I'll personify it a little bit and I'll say their interest and their motivation to bind O2. Does that change at all? They become more interested. Okay, so they see a change. Okay, so let's look at our definition. Binding of an allosteric effector at one site affects the binding properties at other sites. Okay, so I'll go with HB alpha 1. Let's imagine that that is our first oxygen binding site. If O2 binds to HB alpha 1, would everyone agree that HB, I'll just go with beta 1, then becomes more interested in binding O2? Okay, great. So with that in mind, this is an example of our first example, or sorry, this is our first example of an allosteric effector. O2 is an allosteric effector of hemoglobin because when hemoglobin binds to O2, then several of its other subunits become more interested. So O2 is an allosteric effector of hemoglobin. Okay. So that phrase right there is an important one to understand. Now, that also seems a little bit, or it's also important to remember, well, what is O2 from the get-go? O2 is a ligand of hemoglobin. Okay, so not only is it a ligand of hemoglobin, but it's kind of the natural ligand of hemoglobin. So it both binds to it because function, that's what it needs to do. And I know that kind of that personifies it, gives it an intention, and the protein doesn't know any better. It's a protein. Um, but O2 is the natural ligand and it's an allosteric effector. Now, the conformational change induced by the effectors interconvert the R or T state to one another. Now, vice versa. So this can induce the transition from the R state to the T state or the T state to the R state. Now, hemoglobin is a great example of a quaternary allosteric affected protein. The structure of oxyhemoglobin and deoxyhemoglobin are different from one another. Oxygen is an allosteric effector as well as the ligand. Now, that kind of what I was, I guess, belaboring there. But what that means is that this interaction between O2 and hemoglobin is an example of a homotropic interaction. The ligand, the natural ligand, and the effector are identical. Now, to use I guess, kind of an alternative example is, let's say that we have a protein that I'm just going to label it as pro. You could have ligand that binds to that protein, and then molecule X that binds to that protein. Okay. Well, binding of protein X, it's not necessarily causing, or binding of molecule X to this protein isn't necessarily causing any sort of, it's not carrying out any unique function, but maybe that facilitates binding of L, causes a shape change. It enhances the binding affinity. That would be an example of where the ligand and the effector molecule are different from one another. That would be a heterotropic interaction. So a homotropic interaction, or another way to put this is you could say that O2 is a homotropic effector. A homotropic effector. Now, when those molecules are different, which one thing we'll talk about a little bit later, and I'm going to go ahead and give you this term now, BPG. BPG, or bisphosphoglycerate, is an example of a heterotropic effector. So that is a molecule that binds to hemoglobin and alters hemoglobin's ability to bind its natural ligand. So anything that alters or influences the protein's ability to bind its natural ligand is a homo or heterotropic effector. Now, oxygen's just a great example because that is, or it's a simple example because of the fact that the ligand and the effector are the exact same. Okay. Now, here what we have is an oxygen binding curve and kind of a trend that I want you guys to be familiar with. So what we see here is basically three different hemoglobin binding curves. And one thing, we'll get into this a little bit later, but I'm happy to introduce it now, is that there are numbers and numbers and numbers of different hemoglobin variants. For instance, I think the most common hemoglobin variant that people are familiar with would be sickle cell anemia. So sickle cell anemia is a disease state characterized by a single mutation in the structure of hemoglobin. It's, I believe, if I remember correctly, it's a valine to an aspartic acid, or it's an aspartic acid to a valine. It's basically a non-polar residue being mutated to a polar residue. We'll get into it a little bit later, but there are lots of different hemoglobin variants, and those hemoglobin variants have different kind of functions and subtle differences. Now, what we see here are three hemoglobin binding curves, basically overlaid. HB, HB. Now, what I want you to recognize about this is they actually, if you were to describe these curves shape-wise, I would want you to describe them basically as, well, their shape is fairly similar to one another. The only difference is, well, there's a little bit of an artist rendering. Second thing that I want you to recognize about this is they all effectively reach that same kind of saturation point. And typically, I think that this is a pretty common convention for you to see. Um, Even though these proteins don't reach 100% saturation, they get very close to it. And so you have a drawing that effectively shows, oh yeah, they got to 100% saturation. But that's, again, just kind of artist interpretation, artist rendering. Now,
You're so
when it
weird.
if you were to compare these curves to one another, and let's go ahead and just start with the one in the middle, how would you describe the other curves with respect to them? And I'd like to kind of narrow your focus, narrow your terminology. Would you describe them as a shift to the left, to the right, up, down? How would you describe them? And it doesn't, you don't have to refer to, oh, well, I'm thinking of this one. Left or right? Perfect. I want you to think about that because effectively, our hemoglobin binding proteins, or sorry, our oxygen binding proteins, whenever we talk about their binding capacity, it is a shift to the left or it is a shift to the right. So I'll use terminology like when a hemoglobin binding curve shifts to the right, what does that mean? When it shifts to the left, what does that mean? Um, if so, don't look at these and say, oh, well, it looks like it shifts up or shifts down. This is simply a shift to the left or a shift to the right. I want you to keep that in mind. That's very helpful to kind of move forward with. But anything that causes our O2 affinity to go down causes our P50 to go up, and that's characterized by a shift to the right. So that's where we see our curve that's to the right a little bit. Our P50 has gone up because essentially what that means is we need more O2 in order to get our protein to be 50% saturated. Now, anything that causes the O2 affinity to increase, that causes our P50 to go down, characterized by that line right there. Now, so when shifted to the right, the partial pressures, that's a great question, Summer. So I'm going to jump back. The partial pressure in that environment, yes, you could say that it is more. But I want you to think about this and be able to describe it in terms that are protein centric. So hemoglobin centric. So the protein needs more O2 or a higher partial pressure of O2. It's impossible for the Y value to be greater than 1. I mean, I'm thinking ahead because we're going to use similar curves to describe an enzyme's activity. I feel comfortable saying yes to your question, Andrew. Okay, so here it is. This is a question. I'm going to give you 60 seconds to answer this. If you are someone who is, just taps on the screen to be like, question, go away, I'd recommend that you not answer this, or better yet, that you don't just tap on your screen and you say you look at it for a second, you think about it. Because if 100% of the class gets this question right, there will be one bonus point added to everyone's exam too. Okay, what amino acid coordinates the iron at the center of the heme ring? Yes, this again, Morgan. Yes, 1 point. There's 54 people, 53 participants in the Zoom. So there's two people who did not hear me say that. 54 people answered. I'm going to stop this. No, I'm not going to stop it. I'm going to let the clock ride on out. Here we go. We did it. You 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 did it. Add 1 bonus point 2 grades. Great job, everyone. I'm proud of you. And I'm happy because that's great, because I want you to do well. I do not have any sort of interest in people not doing well in this class. So I'm happy about this. Oh, yes. Thank you, Madeline. There is a group me. Madeline added this also to the discussions on our Canvas page, which there have been a couple of discussions. But okay, great job, everyone. Okay, I got another question for you. Thinking about that particular amino acid, what is roughly the pKa? And I know that I told you I did not want you to remember or memorize the pKa values, but this one is kind of unique. I'm not going to ask you explicitly on the test, in part because I'm going to give you the pKa values. What is roughly the pKa for the polar positive amino acid his? I'm going to give you 60 seconds. And I'm confident that you guys can do this. I think definitely the majority will get this right. I'm confident of that. I think it's probably going to be like 2 or 3 for each of the less appealing answers, and then basically none for the least appealing answer. Okay, here it is. Time's up. 54 people answered. Awesome. Histidine is an ionizable amino acid indicated by the classification as a polar positive residue. It has a pKa of approximately 6.1. That would be right. Now, histidine, I bring that up because it's kind of interesting. At a neutral pH, so if the pH was 7, you will still have a small percentage of histidine residues that are protonated. The majority will be deprotonated, but you'll still have some that are protonated. Now, this is significant because what we observe when we study hemoglobin binding proteins is something known as the Bohr effect. Now, the person who developed this theory was a fellow by the name of Christian Bohr, and his studies basically revolved around, well, how does the pH of an environment influence hemoglobin binding? And what I'd like to draw your attention to are these hemoglobin binding curves, which are represented by this, I guess that's kind of a magenta, highlighted at a pH of 7.6, 7.2, and 6.8. So what Bohr observed was that as you decreased the pH of an environment, or you increase the hydrogen ion concentration, he saw that the that hemoglobin's binding affinity for O2 began to diminish. Now, this is significant because this gives you a sense of, well, what are the significant residues for hemoglobin's function? And this is something that really it's pretty standard practice. Anytime you characterize a protein, one of the things that you want to do as soon as you identify what the activity is, you want to begin saying, all right, well, whenever if I have this catalytic assay, if I have this known function for this protein, how does the pH change? Because when you understand how that protein functions with respect to pH changes, either up or down, it gives you a sense of what are the important residues for this enzyme's function or this protein's function. And by seeing this change when we go from 7.6 to 6.8, there's probably some histidine residues that are involved in that. And I say that just because what other amino acids have pKa's, R group pKa's around a neutral pH? And the answer is there's not that many. Now, you can see the same sort of activity depending on other groups that you're altering. But if you think about your polar negative amino acids, like your aspartic acid and glutamic acid, those have pKa's about 3.2. Lysine and arginine, those are closer to 10 and 11. So what Bohr's conclusions was that binding of protons diminishes oxygen binding. Binding of oxygen diminishes proton binding. So there's our P50. When the pH goes down, our P50 goes up because our O2 affinity goes down. Now, after studying this for quite a time, Bohr's kind of conclusions were that the deoxy or T state of our protein had favorable ionic interactions that stabilize the structure. And when you have a protonated form of histidine number 146 at the C termini of the beta 2 subunit, this forms an ionic interaction with an aspartate 94. So anything that complements that protonated form of histidine 146 is going to stabilize that T state. The ionic interaction stabilizes the proton against dissociation, increasing the pKa of His 146. That's kind of interesting because it's almost like doubling down. It's almost like, okay, well, when we have this interaction, then we're going, let's see, when we have this interaction present, then we're going to make sure that that interaction stays present because that's going to cause our pKa to go up. Now, this is something we haven't really talked about that much, but we've always talked about pKa's of R groups and, well, basically different functional groups as being something that's kind of standard. And, it's the R group for aspartic acid has a pKa of 3.2, for instance, and it's not going to change. But does anyone remember this? From organic, the inductive effect. The inductive effect can cause pKa's to vary and to change a little bit. So the inductive effect in a molecule like a protein, depending on the amino acids that make up a polypeptide, an arginine might not necessarily have a pKa of 10.5. It might be 8.2. It might be 5.6. We keep in mind those kind of standard numbers, but the inductive effect can cause pKa's to change. And so similarly, when we have these sort of stable interactions, we can cause pKa's to change, or we can see pKa's to change. But essentially, the protonation stabilizes the T state. Protonation of histidine 146 stabilizes the T state. Now, on the opposite end, whenever O2 binds, the favorable interactions, ionic interactions, are disrupted, in which case that His 146 and aspartate 94 interactions disrupted, returning the pKa to their normal values. And His 146 is deprotonated in oxyhemoglobin at a normal blood pH of 7.4. So it's almost like whichever one gets there first is going to predominate. Is the proton getting there first, or is the O2 getting there first? And whenever that's established, then we're going to have a favoring of one of those two states of our protein. Now, high hydrogen ion concentrations or low pH, which keep those, remember from like Gen Chem 2, those two terms are interchangeable. That's going to favor the protonation of histidine 146. Now, I bring this up just because, and I think that I'll spend a moment on this. Bohr's studies were basically like, oh, I see that whenever the hydrogen ion concentration is higher, well, then I'm favoring the T state. Got it. Hmm. Do I know the structure? Do I know the primary structure of my protein? I do. And okay, here's a histidine, here's a histidine, here's a histidine. What I'm going to do is try to make a mutant protein that doesn't have a histidine in those different locations. That's kind of the process that you go through. Whenever I make a mutation of a histidine at, say, histidine 32, well, my function doesn't really change. Whenever I make a change at histidine 146 to, let's say I mutate this to a something that's non-ionizable, so an alanine. If you had a non-ionizable residue in that position, chances are your oxygen binding curve of this, and I'm just going to label it as HB X, uses your mutant form of hemoglobin with an alanine in that position. That residue is not ionizable. So at a pH of 7.6, 7.2, 6.8, effectively, it's going to look the same. That oxygen binding curve is going to look the same. That variation of that protein is going to stabilize the T state of the protein. Now, protonation of His 146 favors the T state. The T state favors the release of O2. Anything that favors the T state lowers the O2 available or O2 affinity, causes the P50 to go up. Oh. So, okay, here we go. Somewhere. Okay, sorry. Yes, here we go. So I've got the last question for the day. We still have a little bit more to talk about, but hypothetical compound X induces hemoglobin to release oxygen. Which of the following is the most accurate statement based on this? So we've got this hypothetical compound. It favors hemoglobin to release O2 or oxygen. Which is the most accurate? Favors the T state, the R state, and this is the sort of terminology that I really want you to be comfortable with, favoring the T state, favoring the R state. 10 seconds roughly. All right, we're going to call it a day there. Correct. What do we got? Awesome. Great job. So when something induces hemoglobin to release oxygen, that means it's shifting it towards the T state or deoxygenated state. Histidine 146 is not the only residue responsible for the Bohr effect. There are a number of others, but histidine 146 is the one that's very central to it. Now, I don't want you to commit His 146 to memory. I'm not going to ask a question which specific amino acid is responsible for this, but the question that I might ask on an exam would be something like, um, an ionic interaction stabilizing the T state is found between aspartic acid and which other amino acid? And so then you'd have to think, okay, aspartic acid is going to be a deprotonated residue. So for aspartic acid to have an ionic interaction, I've got to have a positively charged residue. So then I'd give you options like lysine, histidine. Well, I'd give you something like lysine, alanine, and tryptophan because what I'm wanting you to understand is the makeup of the amino acids that can have that ionic interaction. No, I think the best question would be for me to ask or to give you options like aspartic acid and histidine, alanine, leucine, isoleucine, because then I'd want you to be able to, you'd have basically two chances of answering that question correctly. One chance is based on, well, I know the identity of my amino acids, leucine, isoleucine, and valine. Those are all nonpolar residues. Histidine's the only positively charged residue. So that is how a ionic interaction must take place. So that's kind of one of the things that I want you to understand. Now, carbon dioxide. We've talked about carbon dioxide quite a bit. It is also an allosteric effector. I think that I probably need to. Okay. So this is an allosteric effector. O2 is an allosteric effector, a homotropic allosteric effector. Carbon dioxide would be a heterotropic allosteric effector. Carbon dioxide basically functions in two ways. One way is it diminishes oxygen binding by decreasing the pH. It increases or it enhances, it augments the Bohr effect. Now, this part of respiration is a part of the production of carbon dioxide. So when you're breaking sugars and fats and everything down, you're generating CO2. And so you need to expel that. You need to get that out of your cells and, well, get it out of your lungs. Now, the CO2 diffuses from the tissues to the capillaries. The hydration of CO2 in tissues and extremities leads to the production or proton production. So CO2 plus H2O is going to yield a compound, or it's going to yield a singular proton and HCO3. Hemoglobin also acts as a CO2 transporter. So the way that it acts as a CO2 transporter is going to be illustrated in just a second. We have an enzyme known as carbonic anhydrase. CO2, H2O produce that HCO3. In erythrocytes, carbonic anhydrase greatly accelerates this reaction. So this is something that can spontaneously occur, but this enzyme, carbonic anhydrase, speeds it up. Now, this is an important concept and an important enzyme for you guys to understand. Carbonic anhydrase in the lungs is where everything is going to be expelled. But in our erythrocytes, here's what's happening. So CO2 is going to react with H2O to produce this HCO3. That HCO3 is going to go into the blood plasma and basically be replaced with the negatively charged Cl minus. Now, the important part about this is that we have the production of a hydrogen ion here. So every time that you get CO2 to react with H2O, you're releasing a hydrogen ion, which is going to the H plus concentration will, as a result, go up, and the pH, as a result of that, will go down. Now, what's going to happen is that HCO3 is going to find its way back into the lungs or back into alveoli and in the lungs, and it's going to be broken down by the same carbonic anhydrase to produce H2O and CO2. That CO2 is going to leave that erythrocyte. It's going to be exhaled. So that's kind of an ideal situation, but how does this actually taking place? Now, the accumulation of CO2 is going to lower the pH in the blood. O2 depleted muscles are going to generate lactic acid, thereby lowering the pH of the blood passing through them. These protons are taken up by hemoglobin as oxygen dissociates. We've already talked about how how proton concentration can influence O2 binding, because as pH goes down and the hydrogen ion concentration goes up, we're going to favor the T state of hemoglobin. Now, the other part of this is that hemoglobin acts as a carbon dioxide transporter. And the way that it does it is through an act or an event known as a carbamation. So a carbamation it falls into the major class or a class of reactions known as a post-translational modification, or a PTM. So this is something that happens to a protein after that protein has been translated. So a carbamation, you could kind of phrase it as a carbamation event, um, is where HCO3 binds to the N-terminal amino group of the subunits of hemoglobin to make what's known as a carbamate. So we have our partially deoxygenated or our deoxygenated hemoglobin that the N-termini of the protein reacts with HCO3 minus. When it reacts with HCO3 minus, here is our N-termini of our protein. Here's effectively that CO2. Well, that HCO3 minus and that N-termini of our protein gives us this product right here. So I'm going to highlight this again in red. This is what is known as a carbamate. So where this CH2 is, that I've just drawn a box around, that would be an alpha carbon of your N-termini of a polypeptide, of that alpha or beta or alpha 1, alpha 2 subunit. So this is going to cause, or it's going to give hemoglobin effectively a CO2 to transport. So this is one of the ways in which that's going to be released. So we have basically two mechanisms where CO2 is influencing um, the pH of the environment. One way is through the Bohr effect with the help of carbonic anhydrase. And then another way is where our CO2 will react with the N-termini of our protein and give us a carbamate and release a proton in the process. So you can kind of think about it as the way that I think is helpful to think about it is we have CO2, CO2. One CO2 will go through the fate of carbonic anhydrase. That carbonic anhydrase will give us HCO3. That goes into the bloodstream. And then this statement up here, well, some HCO3 is carried in the blood. Okay, that's with the help of carbonic anhydrase. Check. Some of that other HCO3 is going to bind to the N-terminal amino groups of the subunits to form carbamates. So the CO2 can also go to carbonic anhydrase and go on to form a carbamate. And then I guess, sorry, it would be a kind of a third outcome where some CO2 will react to the N-termini of our protein to form a carbamate. Now, this reaction aids in the transport of CO2 to the lungs because ultimately, what's the fate of that HCO3 when it gets from the bloodstream all the way to the lungs is it's going to be converted back with carbonic anhydrase into CO2. So this also increases the Bohr effect by releasing hydrogen ions. So the bound carbamates can also form ion pairs, stabilizing the deoxy state of our protein. Now, what I'm going to do right here is go ahead and stop just because 9:49. For the next slide, and actually to kick things off next time, we'll start out with a discussion of carbonic anhydrase, and then we'll work from there. We've got some other things with respect to allosteric effectors. I'm, this lesson was a little bit longer, but we'll work through it a little bit more tomorrow on Wednesday. But I'm going to have some quizzes posted this week for kind of the daily activities, things that we were discussing in class. There will be one posted today by the end of the day, and then Wednesday by the end of the day, and Friday by the end of the day. Those are all going to be due on Sunday evening. I might, if I get them out any earlier, like I'll try to get them all out today, but think about them as corresponding to stuff we talk about on Wednesday and stuff we talk about on Friday. And again, those are all going to be due on Sunday, the 27th at 11 p.m. But with that said, I hope that you have a wonderful afternoon. I hope you have a wonderful day. Madeline added the group me if anyone wants to join that and have discussions. And your learning objectives, I'm going to link that to our main page as soon as I can. I've got a class right now, and then I got something else, but I'll get them to you. I hope you guys have a great day. Thanks for coming to class, everyone. And good job. One bonus point.